right, it says choose the statement below that is true, and then there are these wordy statements. But before we do that, let me briefly go over what is going on here. And again, this is a super brief explanation. So if we have something like NaCl, okay, as our solute, it's going to have Na plus ions and Cl minus ions. And of course, these exist in a lattice, but I'm going to just talk about it this way because I don't want this video to get too long. All right, so we have Na plus and Cl minus. These solute particles are attracted to each other. If we then have two water molecules, these water molecules or solvent molecules are attracted to each other. So in this case, we have this electrostatic interaction of the plus and the minus, or an ionic bond, whatever you want to call it. In this case, we have this hydrogen bonding interaction where the partially negative oxygen interacts with the partially positive hydrogen, such that the bond distance between O and H here is about 1/3. It's about 3 times longer between here and here, I think. So don't quote me on that. But anyway, these are very strongly interacting by hydrogen bonding. So these two things are attracted to each other. In order to get this to dissolve in this, we effectively need to separate these two ions from each other. We effectively need to separate these two water molecules from each other. But what we get in return is that we now have an Na plus with a possibility of interacting with the water. So if we have an Na plus here, this is going to interact with the oxygen, the partially negative part of the water, and I'm not going to draw all of them, but they can be solvating this or completely around it in three-dimensional space. And the Cl minus is going to be interacting with the hydrogens of this water, the partially positive part of this water, because this is negative. So at the end of the day, a solution will form between two substances if the solute-solvent interactions, so this is the solute-solvent interaction, okay, here, because we have water as the solvent and NaCl as the solute, are comparable in strength to the solute, the Na plus attracted to the Cl minus, and the solvent, the water attracted to the water by hydrogen bonding interactions. So if this new form of interaction, in this case the ion dipole interactions between water and chloride and sodium ions, is comparable in strength to overcoming this solute interaction and this solvent interaction, then a solution will form. Okay, and they have to be relatively comparable in strength. None of the other answers say anything like this. They're wordy. I'm not going to read them all. But this is basically what's going on in this question. This says, which of the following statements are generally true? And again, like the last one, we have a bunch of words here. So instead of trying to read through all these answers, let me just go over this briefly. Solids, like ionic compounds and sugar and things like that, tend to be more soluble with increasing temperature. For some things, there's quite a large difference in solubility with increasing temperature, and sometimes between, like where water is liquid between 0 and 100, the difference in solubility between of a solute at 0 versus the solubility of a solute at 100, you could have more than double the amount of solute that will dissolve at 100 degrees C. So that's how it works for solids. However, for gases are going to come out of solution at increasing temperature and turn back into the gas phase. So soda at room temperature, soda is a solution, it has sugar in it of course, but it also is water with carbon dioxide in it, a gas, carbon dioxide. Soda is going to go flat quicker at room temperature, okay, because carbon dioxide is less soluble at room temperature, and it's going to, if you cool it down, may take longer. Now, I'm conflating here the kinetics of it, how fast it takes versus the solubility, which I shouldn't really be doing, but I'm trying to give you a practical example too. But generally speaking, gases are less soluble at elevated temperature, and if you were to heat up a soda water solution, the carbon dioxide would completely evacuate relatively quickly as the solution heated up, because those molecules would have enough energy to fly out into the gas phase. So basically, in general, the solubility of a gas in water decreases with increasing temperature, which is true. But the solubility of a solid generally increases with increasing temperature. There's also, just some words, like the solubility of an ionic solid in water decreases with increasing temperature. Again, the solid tends to be more soluble at higher temperatures. Gases tend to be less soluble. All right, number 14 says, which of the following should have the largest Henry's law constant in water? So Henry's law is the concentration of a gas equals the pressure of a gas times the kH, which is the Henry's law constant factor. Now, effectively, what we're trying to do here is see which one has the most similar intermolecular forces with water, because like dissolves like. So if you go back to question 12, there's a medium length, I guess, explanation of why like dissolves like, and talking about solute, and solvent-solute interactions. And basically, it boils down to three words: like dissolves like. So what we need to remember here is that water is a polar solvent. So in like dissolves like, what's alike is intermolecular forces. So since water is a polar solvent, it's going to dissolve polar solutes. So even gases, okay, they're going to be the solutes, they can be polar. So let's take a look here. Well, bromine is just an atom, so it's definitely non-polar. It's not going to be very soluble in water. Carbon dioxide, there you might have to draw the Lewis structure. We've drawn it a few times already, or at least once already on this sheet, but it looks like this. That's also non-polar because both domains are oxygen, or both domains are the same with respect to carbon, so it's non-polar. Carbon monoxide, I'm not going to try to draw the Lewis structure here. You can draw it. It's a little bit weird because it has formal charges, but that's not the point here. Carbon monoxide has to be polar. Why? Because it's two atoms. One is carbon and one is oxygen, so it's going to be partially negative towards the oxygen. CH3CH3, this molecule is called ethane. It's a hydrocarbon, only contains carbon and hydrogen, so it's non-polar. And then finally, neon is an atom, so it's non-polar. So, like dissolves like. Water is a polar solvent. It's going to dissolve most the polar molecule. Now, if we look at the equation, concentration of gas equals the pressure of the gas times the Henry's law constant. The Henry's law constant being bigger means the concentration of the gas goes up. Said another way, the gas is going to be more soluble in water. Some other classic examples of gases that have high solubility in water, or high KH values, or Henry's law constant values, are HCl and NH3. These are two of the other gases. This case, because it's polar, one side's Cl partially negative, one side's H partially positive, and in this case, ammonia can actually hydrogen bond with the water, so it makes it even more soluble. So basically, if you remember like dissolves like, and remember that what's alike in like dissolves like is intermolecular forces. All right, number 15 says, calculate the molality of a solution formed by dissolving 34.8 grams of lithium iodide in 500 grams of water. So molality is a useful unit of concentration when you're doing temperature studies. So freezing point depression, boiling point elevation are the common ones that we're going to use in this problem set. So molality is moles of solute per kilogram of solvent. The reason using kilograms on the bottom, or masses, is masses don't change when temperatures change, but volumes do. Said another way, molarity, which is moles per liter, liters change. So the concentration of a solution changes over a range of temperatures, which is not good when you're trying to use that as your unit in your formula, because if it's not constant, it makes it difficult to do the math. So basically, using a constant variable like molality is better, although it is another unit of concentration to learn. But in this case, what we need to do is we need to convert the grams of lithium iodide to moles of lithium iodide. So we're going to convert from grams of moles to moles using the molar mass. All right, which we can just add up Li and I to find the molar mass. And then we can convert we can take that and we can divide by the kilograms of water to find the molality. Note that this is a dimensional analysis conversion. This is a new unit. You could, of course, find moles and then divide by kilograms. It's the exact same thing. So if we start with our 34.8 grams of LII times, we want to put 1 mole of LII on the top, and then the molar mass, which we can get from the periodic table, is 133.85 grams of LII times. Now to divide in what looks like dimensional analysis, we simply put a unitless 1. Why? Because that moves the moles over. Now we have moles on the top. We can put kilograms on the bottom. Don't forget, it has to be in kilograms, not grams, so you got to divide that by 1,000. So 0.5000 kilograms. And when you do that math, you find that this is 0.520 molal. So 0.520 molal, which is choice letter B. All right, number 16. These questions could be a little tricky. It says, what is the mass percent of vitamin C in a solution made by dissolving 6.50 grams of vitamin C in 55 grams of water? So mass percent, or any percentage, is the part divided by the whole times 100. Specifically for mass percent in a solution, the mass percent equals the mass of the solute, in this case vitamin C, divided by the mass of the solution, and because it's a percentage, we need to multiply that by 100. So this is basically how we're going to do this. However, what we need to be aware of is the mass of the solution is the total mass of the solution, which is the mass of the solute plus the mass of the solvent. Now, we need to be careful with this because we need to read the question carefully and see, did we get the mass of the solution or the mass of the solvent? You could get either, so you have to read it carefully to figure it out. So let's take a look here. Well, in this case, the vitamin C is the solute, so the mass percent is going to be equal to the 6.5 grams of vitamin C on the top. But if we look at it and we read it carefully, we dissolved it in 55 grams of water. Water is not the mass of the solution. Water is the mass of the solvent. So we need to use this bottom way of doing it as opposed to directly plugging in the mass of the solution. Specifically, we need to take the mass of the solute, 6.50 grams, the mass of vitamin C, plus the mass of the solvent, in this case water, the 55 grams. And we multiply by 100, and when we do that, we find that this is a 10.6% vitamin C solution, which is choice B. All right, number 17 basically asks us for a definition. It says, what is a colligative property? A colligative property is a property that depends on the number of particles in solution, but not the nature of the particles. Said another way, if one were to dissolve NaCl, or one were to dissolve KBr, the amount of the freezing point depression or the boiling point elevation would be independent of which of the two solutes was present, just based on the amount present, the amount in moles, which also takes into account the Van Hoff factor, which is how much things break apart in solution. But the actual identity of the particles, and even whether they're covalent or ionic, doesn't make a difference. It's only the amount or number of particles in solution, but not the nature of the particles. That's just a definition you should remember for this chapter about colligative properties. All right, number 18 says, determine the freezing point depression of a solution that contains 30.7 grams of glycerin, this one with a molar mass, and in 376 grams of water. And then it says some possibly useful constants for water are the Kf, which is 1.863 C per molal. So basically you need to know the freezing point depression constant. So the delta Tf equals I, the Van Hoff factor, times the Kf, the constant you're provided, times M, the molality, okay, which we did in a previous question. If you're confused about I I strongly recommend that you watch the next question, which is a little bit weird, but the next question asks us just about I. I probably should have put it first, but I'm already here, so I didn't. So basically, what we're going to do is we're going to figure out I. Well, if we look here, you have a covalent compound, C3H8O3. And it might be a liquid, but we're going to call it a solid, okay? It doesn't really matter. It's not aqueous, okay? So basically, this is the molecule that we have here. So in this case, what we're going to do is we're going to dissolve it. Well, when you dissolve this compound in water, you get C3H8O3 aqueous. This is now dissolved in water. So why doesn't it break up like an ionic compound would? Well, because it's covalent. Covalent compounds dissolve in water, but they don't dissociate like ionic compounds. How do we know this is covalent? It only contains nonmetals, C, H, and O, or said another way, it does not contain a metal. So we know that it's a covalent compound. So I equals 1. We found I. Kf, again, is given, so we don't do anything for that one. So what we need to do now is find M, which is the molality. To do that, we want to go from grams of glycerin to moles of glycerin. Whoops. And then we want to divide by kilograms of water. Okay. So starting with 30.7 grams of glycerin times, put the molar mass on the bottom, in this case 92.09 grams of glycerin on the bottom, 1 mole of glycerin on the top, times. Now just like we did before, we put a unitless 1 here. This moves the moles, the mole of glycerin over. Okay, the moles move over. Then on the bottom, we have to put the mass of the solvent in kilograms. So you can't put in 376 grams. You got to divide that by 1,000 and put in 0.376 kilograms. And when you do that math, you find that it's 0.887 molal. We now have everything we need to plug in. So the delta TF is going to be the I, which is 1, times the Kf, which is 1.86 degrees C per molal, times the molality, which we just found, which is 0.887 molal. Multiply through, and we find that delta TF is equal to 1.65 degrees C. Okay, so this is the freezing point depression. Note that this solution will freeze at negative 1.65 degrees C, because the normal freezing point of water is 0, and we're going to be 1.65 degrees C less than 0, so negative 1.65 degrees C. Alright, so if you watched the previous question already and you're confused about the Van't Hoff factor, this is probably a better place to start, and I probably should have reordered these questions, but I didn't think about it until I got into the video. So it says, identify the solute with the highest Van't Hoff factor. So Van't Hoff factor is important in colligative properties because it's the number of particles in solution that matters. So Van't Hoff factor is simply a multiplier by how many particles are actually in solution when you dissolve something. And because ionic compounds dissociate in water, it's very important to realize how they dissociate so that we can determine how many particles are in solution. So I'm going to do that for each of these, assuming that they're all solids at the beginning, even though, like in the previous example, glycerin is probably a liquid at the beginning. That doesn't really matter because it's not aqueous. So Ki, solid, and it definitely is solid because it's ionic, yields K plus aqueous plus I minus aqueous. So when you dissolve ionic compounds in water, they dissociate into their ions. Don't forget your charges, okay? Your charges of your ions, which are based on, this is 1A and this is 7A. You may need to review that, but that's not super important here. What's super important here is it breaks up into 2 things. So I equals 2. Said another way, if you have a 1 molal solution of Ki, you'll really have a 2 molal solution of particles because you have twice as many things in solution. So I is that corrective factor, effectively, for how many things are in solution. All right, C6H12O6 solid. This compound is covalent. I'm going to write it below just for space reasons, but this is a covalent compound. It does not dissociate. Just like glycerin in the previous example, this is C6H12O6 aqueous, okay, and it does not dissociate. It dissolves, right? It's dissolved in water, that's what aqueous means, but it does not dissociate because it's covalent. So for covalent compounds, I equals 1. Note that this is called an electrolyte because it's an ionic compound that dissolves and dissociates into its ions. This is called a non-electrolyte because it's a covalent compound that dissolves but does not dissociate. So if you had a non-electrolyte solution, that would also have a Van Hoff factor of 1, and that comes up a little bit later on. AlCl3, kind of an interesting example because it'll probably react with water, but that's okay, we can do it anyway. AlCl3 solid yields Al3 plus aqueous plus 3Cl minus aqueous. So the aluminum 3 plus, it's 3A, so it's 3 plus, dissociates from the 3 Cl minuses. We still need a balanced chemical equation. All right, there's 3 Cls, so you have to have 3 Cls over here. So in this case, you have 1, 2, 3, 4. So one of these and 3 of these, a total of 4 things in solution. So in this case, I is equal to 4. Next thing, magnesium sulfate. This brings up an important example. All right, I'm going to write the magnesium sulfate up here. The magnesium sulfate is an important example because we have a polyatomic ion. So if we start with magnesium sulfate, solid, the magnesium sulfate will dissociate, the metal in the polyatomic ion will dissociate, but the polyatomic ion stays intact. So what you end up with is Mg2 plus, magnesium is a 2A metal, aqueous, plus SO4 2 minus aqueous. So the polyatomic ion and the metal dissociate, but the polyatomic ion stays intact. It's sulfate over here, it's sulfate over here. In this case, I is equal to 2 because we get 2 things in solution. Calcium chloride, so if we have CaCl2 solid, it breaks up into Ca2 plus, another 2A metal, just below magnesium, aqueous, plus 2Cl minus aqueous. Again, just like the AlCl3, you have 2 Cl minuses because it's Cl2, so you get 2 Cl minuses, and you get a total of 1, 2, 3 things in solution, so I equals 3. Back to the original question that we read quite a long time ago now. It says identify the solute with the highest Van Hoff factor. The one with the highest Van Hoff factor is choice letter C because it's the only one with 4. All right, number 20 says, choose the aqueous solution that has the highest boiling point. These are all solutions of non-volatile solutes, and you should assume the ideal Van Hoff factors where applicable. So we need boiling point elevation. So boiling point elevation, delta TB, the change in boiling point, equals I times KB times M. This is very similar, it's basically the same as the freezing point depression constant that we used in question 18. But in this case, what the difference is we use the boiling point elevation constant, but everything else is the same. It's also important to note that in this case, all of our solutions are 0.1 molal. Said another way, the molality of all of our solutions. I should have been more clear because I was assuming that you had seen question 18, but if you haven't, I is the Van Hoff factor, KB is the boiling point elevation constant, which is constant, of course, and M is the molality. But in this case, the molalities are also constant. Said another way, this whole part of the equation is constant because this is a constant and these are all the same, so that's constant. So the only difference is I. Now, in this case, I am not going to write all these out as reactions. I did on the worked out answers that you can see, but I did it quite extensively in question 19, and I don't want to take forever to go through this one. So in this case, we have BaCl2. This is an ionic compound. It contains a metal, and it's going to break up into Ba2 plus and 2Cl minus, so I is equal to 3. C6H12O6 was in the previous question. It's covalent. It does not contain a metal, so the Van Hoff factor is 1. Another way of saying that is this is a non-electrolyte. AlCl3 was also in the previous question, and we found that it breaks up into Al3 plus and 3Cl minus. So I is equal to 4, and LiBr is an ionic compound again, and we found that it breaks up into Li plus and Br minus. We didn't find that before, but that's what it will do. Okay, again, these compounds have metals, so they are ionic. If I said this was covalent, I meant to say that it was ionic. So I is equal to 2. So in this case, the one with the highest Van Hoff factor is going to have the highest change in boiling point because the molalities are constant. So the answer here is choice letter C, which is I equal to 4, or the Van Hoff factor of 4. All right, it says a covalent compound, non-electrolyte, is found to have a molar mass of 598 grams per mole. If 0.0358 grams of the compound is dissolved in enough water to make 175 milliliters of solution at 25 degrees C, what is the osmotic pressure of the resulting solution? So we need to know the formula for osmotic pressure. Osmotic pressure is pi equals ICRT. Okay, I'm not going to go into a ton of detail about what osmotic pressure is, but I do want to remind you that nature tends to dilute things. So if you have a semi-permeable membrane and you have a more concentrated solution and a less concentrated solution, water from the less concentrated solution will permeate that semi-permeable membrane and dilute the more concentrated solution. If you do this in a U-shaped tube, you can actually see how this would generate pressure based on a difference in height between the two solutions. For now, we're just going to try to solve this. Now, this is basically the ideal gas law. Pi is pressure, right, B, and C is concentration in molarity units, which is moles per liter. So this takes into account both moles per liter. Do note that it does have the I in it because this is a colligative property, and of course the ideal gas law does not have the I in it because gases are not ionic, but also because they wouldn't dissociate. I don't know. We don't need to get into that. Anyway, let's go ahead and try to solve this. So pi, osmotic pressure, I, Van Hoff factor, C is the concentration in molarity, R is the ideal gas law constant, 0.08206, and T is the temperature in Kelvin. So a couple things that we need to do. First thing, we need to know I. Well, if this is a covalent compound, a non-electrolyte, I is equal to 1. Covalent compounds do not dissociate when they dissolve in water. C is the concentration, and that's where we're going to spend the most time because we need to find the molarity of this. So we have the grams of this compound. We're going to convert it to moles of this compound using the molar mass, and then we're going to divide that by the liters of solution because molarity is moles per liter of solution, moles of solute per liter of solution, unlike molality, which is per kilogram of solvent. So if we start with the grams, this is 0.0358 grams of this compound, times, we put the molar mass on the bottom, the 598 grams on the bottom, the 1 mole of whatever this compound is on the top, times a unitless 1, just like when we were calculating molality and molarity before. This just moves the moles over, and then we have to put the volume in liters on the bottom. So not 175 milliliters, but 0.175 liters. When you do that math, you find that this is 3.42 times 10 to the minus 4 molar solution. So we have I, we have C, R is constant. Now we got to get T. So to get T, we have to take the 25 and we have to add 273 or 273.15 if you like. I'm just going to call this 298K, okay, for our temperature. So now we can plug in pi equals I, it's a non-electrolyte, so I is 1 again, times C, we just found that, 3.42, times 10 to the negative 4, times R, which is 0.08206, and that's liter atmospheres per mole K. The same constant we use in the ideal gas law, times the temperature in K, which is, 298K. When you multiply that through, you find pi is equal to 0.008365. And if we look, that's none of these answers. Okay, so why is that? Well, what we need to be aware of is that this is in atmospheres, because the unit of pressure here is atmospheres. And if we look at our answers are all in torr. And the reason for that is there's a really small number of atmospheres, so probably torr is a better unit here. So we need to convert this atmospheres to torr. Specifically, we need to take the 0.008365 atmospheres times, for every 1 atmosphere on the bottom, it's 760 torr on the top. And when you do that math, you find that it's 6.36 torr. So the answer is choice letter D. Thank you for watching this video. I hope that you found it helpful.